Welcome to today's video. Encryption is the invisible force that protects everything in our digital world, from private text messages to your bank account, even to national secrets. For decades, encryption has been our ultimate safeguard, built on mathematical systems that seemed unbreakable. But today, we face a game changer: quantum computers, a new kind of machine with the power to unravel the very fabric of our digital security. How do they work? Why are they so powerful? And what does this mean for the future of cybersecurity? Let's dive in. To understand why quantum computers are such a threat, we first need to understand encryption itself. The story begins over 2,000 years ago with Julius Caesar. He developed the Caesar cipher, a simple but ingenious technique to protect his military messages. Each letter of the alphabet was shifted by a fixed number of spaces. For example, A became D, B became E, and so on. Back then, this was enough to keep prying eyes at bay, but as time went on, ciphers became more sophisticated. By the Middle Ages, we had polyalphabetic ciphers that rotated between multiple shifting alphabets, making messages harder to decipher. Then, in the 20th century, encryption took a quantum leap with the Enigma machine. The Enigma machine was a marvel of mechanical cryptography. Its series of rotors scrambled text into highly complex codes that were believed to be unbreakable. Every day, the settings of the machine changed, creating billions of possible configurations. Breaking the Enigma required nothing short of genius and the computational power of one of the first modern computers, built by Alan Turing and his team. But today's encryption systems make the Enigma look like child's play. Modern cryptography, like RSA encryption, relies not on mechanical devices but on the unyielding complexity of mathematics. RSA encryption begins with two large prime numbers, which we'll call P and Q. These numbers are multiplied together to produce another number called N. This number, N, becomes part of what's known as the public key, which anyone can use to encrypt data. But to decrypt the data, you need to know the original prime numbers P and Q, which are part of the private key. The security of RSA lies in the difficulty of prime factorization, breaking the number N back into P and Q. Think of N as a padlock and P and Q as the keys. It's easy to lock something using the padlock, but without the keys, opening it is nearly impossible. For small values of N, factorization is straightforward. For example, if I give you the number 15, you can quickly determine that its prime factors are 3 and 5. But as N grows larger, the problem becomes exponentially harder. With a 2048-bit RSA key, a common standard today, it would take classical computers millions or even billions of years to factorize N. This is what makes RSA encryption so reliable, or at least it used to be. Enter quantum computers, a new kind of machine that doesn't play by the same rules. Classical computers, like the one you're using to take notes, use bits, the smallest units of information that can exist as either 0 or 1. Think of them as tiny light switches that are either off or on. But quantum computers use qubits, and a qubit can exist in a state of 0, 1, or both simultaneously, thanks to a phenomenon called superposition. Imagine flipping a coin. A classical bit is like a coin that has landed on heads or tails. A qubit, on the other hand, is like a coin that's still spinning. It's both heads and tails at the same time. But the power of quantum computers doesn't stop at superposition. They also make use of a phenomenon called entanglement. When qubits are entangled, the state of one qubit is directly linked to the state of another, no matter how far apart they are. Together, superposition and entanglement allow quantum computers to process information in ways that classical computers cannot. Imagine trying to find the shortest path through a maze. A classical computer would evaluate each possible path one by one. A quantum computer, on the other hand, would explore all possible paths simultaneously, arriving at the solution much faster. One of the most groundbreaking breakthroughs in quantum computing is Shor's algorithm. Developed in 1994 by mathematician Peter Shor, this algorithm is designed specifically to solve the problem of factoring large numbers, the very problem that RSA encryption relies on. Here's how it works. First, we select a random number called A, which is co-prime to N. This means that A and N share no common factors other than 1. Next, we define a modular function, f of x, which equals a to the power of x mod n. This generates a sequence of numbers that repeats periodically. The key to breaking RSA encryption lies in finding the period of this sequence, the point where the numbers start repeating. For small values of n, this is easy. For large values, it's nearly impossible with a classical computer. However, a quantum computer can use the quantum Fourier transform to find the period exponentially faster. Once the period is known, it can be used to calculate the prime factors of n. This means that a sufficiently powerful quantum computer could break RSA encryption in hours or even minutes, rendering systems like online banking, encrypted emails, and cryptocurrencies vulnerable. This is why researchers are racing to develop post-quantum cryptography, new encryption methods that are secure against both classical and quantum attacks. One promising approach is lattice-based cryptography, which relies on the difficulty of solving problems in high-dimensional geometric spaces. Imagine trying to navigate a maze, but instead of 2 dimensions, the maze exists in 500 dimensions. Another method is code-based cryptography, which uses error-correcting codes to secure data. These codes are already widely used in telecommunications and are known to be quantum-resistant. Hash-based cryptography, which relies on the properties of cryptographic hash functions, is another strong contender. The transition to post-quantum cryptography will be challenging. Every system that relies on encryption, from banks to hospitals to smartphones, will need to be updated. This requires not only new algorithms, but also new hardware and protocols to implement them. Quantum computing represents both a threat and an opportunity. Beyond breaking encryption, quantum computers have the potential to revolutionize fields like medicine, materials science, and artificial intelligence. For example, they could simulate molecular interactions with unparalleled accuracy, accelerating the discovery of new drugs and treatments. In materials science, they could help design new materials for renewable energy. In artificial intelligence, they could enable faster and more efficient training of machine learning models. The quantum revolution is both a challenge and an opportunity. You have the chance to shape how this technology is developed and applied, ensuring that its benefits are realized responsibly. The race to secure our systems against quantum threats is one of the most important technological challenges of our time. Let's rise to the challenge and ensure that the quantum revolution is a force for good. Thank you for watching.
Subscribe it. Technomics.